this lesson we're going to look at confidence intervals for means. So recall when we looked at creating confidence intervals with proportions, we sort of used the form point estimate plus or minus margin of error. And we developed this notion of margin of error, and we found it was composed of two parts, right? It was the critical value and the standard error. So for proportions, we wrote it as p hat plus or minus z star times the standard error proportion. And then if we replace standard error proportion with its formula, we finally got p hat plus or minus the critical value times that standard error term, which is the square root of p hat times 1 minus p hat all over n. Let's develop this same notion for sample means. So instead of a point estimate, which is what we call p hat, we're going to use the sample mean. And I suppose we could have been more general with our formula and had it as statistic plus or minus the margin of error. So with proportions, our statistic was our point estimate, right, with p hat. And as you hopefully recall from an earlier lesson, the standard deviation of the sample mean is sigma divided by the square root of n. But before we go any further with this or work any problems, we need to make an observation. So what happens when we don't know the population standard deviation? And why would you, right? So think about it. You're trying to estimate the population mean by taking a sample, right? So in what sort of world do you not know the population mean, but you do know the population standard deviation? You won't, ever. So this form here, as it stands now, is useless, maybe a strong word, but we're never going to know that sigma. So what do we know now that I've given you what appears to be a completely useless formula? Well, the best we can do is use the standard deviation from the sample. But this doesn't quite work. It's promising though, right? Recall from the reading that for a given population, that sigma is fixed. However, S varies from sample to sample. So we actually don't get the normal distribution. We get what's called the student's t-distribution, sometimes called just the t-distribution. Notice this t-distribution. I'm going to simulate this in StatCrunch, and I'll provide the applet here within this module for you to be able to play with. As we get closer, this is the t-distribution, which is the black color distribution, and the red color is the normal distribution that's superimposed. So we have n equals 2. And we can see that it's similar in its shape, but there are some differences. In particular, there's a thickness in the tails of the t that we don't have with the normal. But as I increase n, here's n equals 2, and then equals 6, n equals 11, what do we notice as I'm increasing these? Right, it's getting closer to the normal. In fact, once you get above 30, they're basically right on top of each other. So it's this extra thick tails. It helps to account for the variability of the sample standard deviation. So unlike that normal distribution, the t-distribution is affected by n, and it's its only parameter. So notice this applet uses a slider labeled df, and that df stands for degrees of freedom. And notice, like when df is 1, n is 2. df is 5, n is 6. So degrees of freedom is just n minus 1. So generally you're given an n, and you have to find degrees of freedom. Now this is particularly important if using the table to find our t statistic. If using the TI-84 or StatCrunch, it's going to compute this for you automatically when you put in the value of n when constructing the interval. So let's get back to developing our formula for our interval about the mean. So instead of a z statistic, we're going to use the similar t statistic that we have degrees of freedom that we'll need to look up in a table, or will be computed using technology. So our model for constructing intervals about the mean is going to be x bar plus or minus the t statistic, where t equals x bar minus mu over the standard error of x bar divided by the square root of n. So again, most of you are going to be relying on technology to crunch this out, but I want you to see sort of behind the scenes what's happening. It'll give you a better sense of what this error term is composed of. And as usual, there are some conditions that need to be met before we can safely use the t-interval or t-distribution. So it's hard to verify, but the samples need to be independent. We often have to assume this. Samples should ideally be a simple random sample. And our 10% condition, a sample needs to be smaller than 10% of the population, for the same reasons we had with proportions. And we need to sample from a nearly normal distribution, or if n is bigger than 30, that's covered. So if the sample is less than 30, we need to check to see if the distribution looks like it could have come from a normal population. We should also check for any outliers, symmetry, all those things we did earlier in lessons is coming into play here. We looked at box plots to test for outliers and symmetry and skewness. We looked at normal probability plots. We looked at histograms. So the first three conditions are usually met in these textbooky type problems, experiments conducted by trained researchers. It's this fourth condition that we'll actually be commenting on in the example problems that follow. So especially if it is not stated the data came from a normal population. So let's work out an example.